Today, we are fortunate to be updated regarding some of the research findings of sustainability solutions in the concrete industry. I am honored and privileged to introduce Dr. Randolph Kirchain, Principal Research Scientist and Co-Director and Interim Executive Director of the Concrete Sustainability Hub at the Massachusetts Institute of Technology. Dr. Kirchain's research and teaching aim to improve materials technology decisions by characterizing the economic and environmental impact of those decisions. That impact may derive from changes in the performance of the products into which these materials are transferred and/or in the systems in which they are produced, used, and eventually discarded. Dr. Kirchain has authored over 200 publications in refereed journals and conferences. He has been awarded the American Iron and Steel Institute's Top Technical Achievement Award, the General Motors Technical Achievement Award, and the TMS Recycling Technology Award. Dr. Kirchain earned his Bachelor's of Materials Engineering at the Georgia Institute of Technology in 1994 and his Ph.D. in Materials Science and Engineering from the Massachusetts Institute of Technology in 1999. Dr. Kirchain and his colleagues are some of the leaders directing North America's transition towards carbon neutral concrete. Please join me and welcome Dr. Randolph Kirchain.
Thank you very much, Bill. And my name is Randy Kirchain. I'm one of the co-directors of the Concrete Sustainability Hub at MIT, or what we refer to as the Hub. The Hub is jointly sponsored by the Portland Cement Association and the Ready Mix Research and Education Foundation. What I wanted to talk to you about today was research both done by ourselves and others throughout the globe to not only identify opportunities to reduce the footprint of cement and concrete, but to actually identify those areas where concrete can be a part of the sustainability solution. Before we get into talking about some of those pathways, though, I thought it would be useful just to provide a little bit of context about why this is important. Concrete is a large industry, but it helps to just put a few numbers on it to give you a little bit of context. So for the last decade or so, global cement production has hovered at around 4 billion tons per year. And that clearly sounds like a large number, but a couple of other facts give you even a better appreciation of just how large the industry is. So that 4 billion tons of cement translates into nearly 30 billion tons per year of concrete that is produced and used. And as a point of comparison, the steel industry produces about 1.8 billion tons per year, so about 15 times less. Now, that scale of an industry comes about strictly because of the bundle of properties that concrete provides. It's a versatile material. It's able to be used in deep wells and underground pipes, as well as overpasses and bridges. It's a durable material. It is a material where the tools and processes have been developed so that contractors can construct it. That is, it's constructible in that varied set of applications. It's also quite pervasive because of how available the raw materials are. In most parts of the world, those raw materials are available to make cement and concrete. And ultimately, all of these things come together to make it an economical choice, that it provides value in the applications that it's applied, providing significant value per dollar that is spent. So that explains why the industry is as large as it is. There are also a number of forces at play that seem to be continuing the use of concrete, if not increasing the intensity of its use. And just to touch on a few of those that are key drivers for future use of cement and concrete are things like meeting sustainable development goals, or addressing affordable housing shortages, or decreasing the cost from natural disasters. It might not immediately be apparent as to why you would attach sustainable development to concrete, but the fact is that all of these types of goals require some level of investment in an effective and robust infrastructure. We can't deliver clean water, or we can't produce clean energy. We can't even deliver effective healthcare if we don't have a cost-effective infrastructure in place for those. In fact, analysis that was published in 2019 in Nature Sustainability found that infrastructure was tied to every one of the high-level 17 sustainable development goals put out by the UN, and in fact are tightly tied to over 70% of the specific targets and metrics to accomplish those goals. Now, we may often think of this as something that's more pertinent for the developing world, but all of us are aware of the ongoing policy discussions to spend anywhere from $1 to $2 trillion to upgrade our infrastructure, everything from bridges and roads to better hospitals. So again, there are many materials that will play a role in providing that infrastructure, but given our current industry and our current construction industry, concrete will certainly be a part of that. Another aspect of that is addressing affordable housing shortages. You may have heard estimates such as globally we need to build 2 billion more housing units through the rest of the century in order to meet population growth. And obviously those needs are particularly acute in the developing world, but like these headlines here point to, it is also a very real issue in the United States and in North America, and that is to provide affordable housing. Freddie Mac estimates that if we continue the current rate of construction, we may be short as much as 4 million units by the end of the decade. And actually, I recently saw an estimate by the National Association of Realtors that suggests that that may be even larger gap in that. And so again, many materials will play a role, but currently part of the solution would be concrete to be able to meet this affordable housing shortage. And then finally, a final pressure to think about that continues to push us to use concrete is in responding to what seems to be somewhat permanent trend of increased instances of severe natural disasters. 2020 was the 6th year in a row where the United States experienced more than 10 events that caused at least $1 billion in damages. And in fact, across the entire portfolio of natural disasters that occurred last year, the total amount of damages reached almost $100 billion. And spending simply to repair the damage after the effect is not the responsible strategy here. We need to shift to building more robust structures and more robust infrastructure so that we can reduce that cost and reduce the time to recovery. Again, many materials will play a role, but one of those materials will almost certainly be concrete. So you see a number of trends that are continuing the use of concrete intensely out into the future. It's not surprising, therefore, that we see calls out in both the popular press and even the trade press associated with architecture and construction that raises a question of how can we reconcile this intense use of this industry with the climate impacts that are associated with it. In fact, it sort of poses a existential question. Is it possible to continue to use concrete to meet development goals while also meeting sustainability goals? And so what I wanted to share with you, as I mentioned, is some of our own research and research from others that have helped to try to identify what some of those pathways are and find areas where there is real possibility for concrete to contribute to sustainable solutions. I want to make a fairly critical point, and that is that when we talk about the sustainability performance of any material, concrete or any other material, we can't just focus on the material's production stages. Obviously, it is critical to understand what the impacts of extracting raw materials are, or emissions due to energy consumption or process chemistry. But materials choices affect environmental performance not only at that stage, but also many other activities of what we refer to as the life cycle of that material or of that product. The materials properties influence fuel use during processing. They influence the efficiency with which materials can be applied during design and construction. Materials properties alter the properties of the products or the structures that they're incorporated into. They change the amount of energy that's used by that structure. Or they may be chemically active, or they may directly interact with the environment. And finally, materials choices that we make impact the end-of-life performance of a product. They impact how effectively those materials can be recollected and repurposed into a second valuable use. Now, a lot of the focus of evaluating environmental performance for materials looks at just these first couple of stages. And you may have heard the term embodied impacts, and I will use that in the rest of the presentation as well. But my point here is that, again, when we talk about the environmental performance of materials, we have to think about the whole life. Now, having said that, let's talk about what are some of the strategies, both in the embodied and the rest of the life cycle, to improve the footprint and ultimately make concrete a sustainable solution. And I'm going to break that down into three headings. First is one about how we can reduce the footprint of cement production. Secondly, what are some of the opportunities to reduce the footprint during concrete production and its application? And then finally, the one that we are most excited about within the hub is how do we identify those applications that are net negative, that where the use phase or end of life phase impacts actually provide benefits that are larger than whatever burdens occur during the embodied stages of the life cycle. But let's begin by talking a little bit about what some of the opportunities are for reducing the footprint of cement production. This is a schematic that comes from a report by the World Business Council on Sustainable Development, the International Energy Agency, and the Global Cement and Concrete Association. The process for making cement starts in this lower left-hand corner down here with the quarrying of raw materials, typically limestone. They're crushed and then fed into a furnace, a rotary kiln, where they are processed at over 1400 degrees C to produce a product that we refer to as clinker. That clinker is then subsequently crushed and blended with other minerals to make the powder that we refer to as cement. So this group of WBCSD, IEA, and GCCA have developed a roadmap of what some of the strategies are to reduce the footprint of cement manufacture. And in particular, they have identified 4 points of leverage. That is, improving thermal and electrical efficiency within the facility, basically bringing it up to best-in-class performance. Applying alternative fuels, that is, fuels that are often bio-derived, but in one way or another don't generate the same fossil carbon output as conventional fuels. Strategies to blend in other types of minerals and therefore reduce the amount of clinker that is required to produce the cement. And finally, implementing carbon capture and storage technologies. So these are technologies you might associate or have heard about for power plants or maybe other large industries like steel production that can be applied also in cement production in order to capture and sequester carbon before it's released. So what has this group found as what are some of the possibilities for these strategies and which ones would be most influential? So overall, this group has developed a roadmap of some very realistic implementations of these types of technologies that they feel could reduce overall cement production emissions by 24% by 2050. And that 24% is an impressive target because what they mean by that is 24% lower than roughly current levels of emissions, despite the fact that they anticipate the industry to grow by its production by about 20% over that same time horizon. The chart in the middle here gives a pretty good visual image of which of these strategies are most influential. And the first one and highest priority one is clearly carbon capture and storage. That would provide about 50% of that 24% reduction. The next one is what I referred to previously as clinker substitution. Here is referred to as a reduction of its clinker to cement ratio. And that can provide another more than 1/3 of that reduction. Now, it's important, even though these others are smaller, that they are also an important part of the portfolio. It's important that technologies are put in place that allow for alternative fuels to be used and for the facilities to be brought up to best-in-class technology. So overall, there are some real important potential here for significant reduction. Think about what are some of those stages of production, and that is the production of concrete. So in order to understand what are in these sort of 5 here, so different types of aggregates, binder, which is classically Portland cement as produced in the way I described earlier, but can be other cementitious materials as well, water, and then what are referred to as admixtures or specialty chemicals that provide specific properties either during construction or use. Now, these mixtures have generally been designed to provide typical technical performance metrics. So that is strength or stiffness or some form of constructability or durability. What we think is exciting is that because it hasn't really been managed previously, there should be large opportunities to design these mixtures to continue to provide those structural performance metrics, but while also reducing GHG emissions. So what are some of the ways we can do that? Well, first, before talking about that, just to help contextualize that a little bit, it's useful to understand where the big drivers of CO2 emissions associated with concrete are. And I found that a really good way to bring that message home is first by comparing it to where the mass in that mixture lies. Mass, the mixture is dominated by aggregates, but the emissions, as you can see, it's almost flipped and is dominated by cement production. You have another 5% associated with the mixing or the processing and transportation of materials, and about another 16% or so that comes from the sourcing of other raw materials like aggregates. So given this picture, what are some of the opportunities to further reduce the footprint of concrete? Well, one of them actually comes from a fairly surprising source, and that is that it is possible during, and this is actually commercially implemented today, is to actually inject CO2 during the mixing process, and in doing so, bind up some amount of CO2 in the concrete mixture. Some other strategies that have to do more directly with some of the constituents are around in terms of aggregates. One is to carefully source and process aggregates to maximize the packing density of those and therefore minimize the amount of binder. So remember, the binder was a strong source of CO2. Another one that we are particularly excited about is the development of technology to produce synthetic limestone aggregates from captured carbon. Given that the conventional Portland cement is a potentially significant source of CO2, strategies to reduce the amount of that, we refer to these as the blended cements that make use of other raw materials. Any cement produced with, say, carbon capture that will lower its general footprint, or using other cementitious materials, so-called supplementary cementitious materials, to reduce the amount of cement that is being used as a binder. And finally, there is an important role for these admixtures to enable many of these strategies and still be able to generate the properties during construction or use. A very important one is the use of other binders in addition to Portland cement. So these may come from natural sources, such as natural pozzolans or calcined clays, or they may come from waste sources, such as fly ash or granulated slag, or even properly processed post-consumer glass. All of these can serve a role to reduce the amount of that clinker that needs to be produced and therefore the emissions that are associated with it. Now, it probably obviously raises the question, if these are out there, why do we not see more of their application today? And I should say that they are applied widely today, but there is opportunity to increase that use. I would sort of highlight two key challenges here. One is about standards, and that is that one of the key barriers is often the way that standards or codes are written up that prescribe a certain amount of Portland cement that has to go in the mixture. That obviously immediately puts a limit. The second one is often perceived risk, and that is because the supply chains for these materials may not be as well developed or at least well tailored to the construction market as Portland cement, firms may often perceive there to be additional risk in incorporating them into their portfolio. So to de-risk this situation, we feel that an important thing is the development of additional information so that firms know what is available when and where in order to reduce that sourcing risk. So another strategy that I mentioned that we are particularly excited about is the use of captured carbon in cement and concrete production. I mentioned CO2 injection during the concrete production, but what I'm talking about here more generally is the combination of CO2 with some kind of an alkaline reactant. It could be a seed amount of cement, it could be a brine solution, it could be some forms of industrial waste that mineralize when combined. That is, they bind the CO2 in order to produce some type of construction product. That could be a granulated binder like I'm showing here on the left. It could be the concrete that I mentioned earlier. But we think a particularly exciting direction is the growth of synthetic aggregates shown in the middle here. There are a couple of firms that are doing this commercially at limited scale today. Also, I should say that we're not the only people that are very excited about the potential of this technology. This plot here comes from the Center for Climate and Energy Solutions. The y-axis here and the lines represent the market size for in dollars for a number of technologies that can be used to capture carbon and apply it in some application. So that is as opposed to simply capturing it and sequestering it somewhere. So you may have heard about things like the use of CO2 to feed algae to produce fuels, or as I just mentioned earlier, the use of CO2 in concrete mixing itself, or as the yellow line shows here, is the growth of aggregates. Now, the line represents the potential market size in dollars. The circle, particularly the circle at the end of that line, is this group's estimate of the amount of CO2 that could actually be sequestered or mitigated through this application. So you can see why there is some real excitement about that particular strategy. Now, I just want to reiterate this point that I made earlier, and that is that one of the biggest barriers to seeing more application of these innovative mixtures and these innovative technologies is the use of prescriptive standards. And so we think it's really critical that the industry move toward performance-based specifications. That is, specifications where the composition of the mixture is not specified, but rather the performance that it would deliver. We think that if specifications are developed in that way, it will increase the amount of potential innovation here. It'll allow producers and users, that's architects or construction firms, to make the trade-offs between performance, environmental impact, and cost. So a really critical barrier that needs to be removed to drive this type of innovation. Now let's turn to the last category, and that is, so we have some opportunities to reduce the footprint of cement production. We have some opportunities to reduce the footprint through concrete production. What about the possibility of concrete to provide carbon reduction benefits during use and end of life? So I just want to kind of reiterate what I mean by this is that that material that is chosen at the beginning of life can have real implications, real impacts on the emissions that are associated with these later stages of the life cycle, real impacts during design and construction, real impacts during the use of the product or structure, and ultimately real impacts on end of life. Now, this is actually the largest portfolio of our work, is understanding how those material choices impact these parts of the life cycle. And so there are a number of different examples I could share with you. I thought that the most fascinating one is actually about pavements. And so I want to initially acknowledge that that's probably a sentence that you never thought anyone would say, which is that it's the material choice in pavements is a fascinating topic. But I think that the reason that it is in fact quite fascinating is because of that irony, that we often think that the materials that go into pavements, certainly they have some impact in their production, but once they're in the road, they're there. They simply sit there. What could their impact be during that so-called use phase of the road? But it turns out that we and others have uncovered a number of ways in which that seemingly passive material has some significant ways in which it impacts the environment. So one way that materials impact the environment is through their surface and thermal properties. So the one that I'm emphasizing in this figure here is so-called albedo. That is the amount of energy that a material reflects back into the environment or absorbs as heat into itself. You can see this IR image on the left showing how different the amount of heat that's associated with two different pavements, a darker one in the background and a lighter one in the foreground. Another way that pavement materials interact with their environment during life, for concrete that is so-called carbon uptake or carbonation, and that is the absorption of CO2 during the life cycle. And a final one is one that I often have found that very few people think about, and that is that the material properties of the pavement actually impact the amount of fuel that the vehicles that drive upon that pavement use. It's what we refer to as pavement vehicle interaction. So I'd like to kind of unpack a few of these to give you a sense of how our research has provided some quantification of what these impacts can be. So let's talk about carbon uptake, or what's historically been referred to as carbonation. This is a natural process that happens when CO2 reacts with hydrated cement in the concrete. It is effectively the same type of process I was referring to earlier that would create those synthetic aggregates. In that case, we would use chemistry in order to accelerate the process. Here we're talking about a comparatively slow but natural process that happens throughout that the life cycle of the concrete structure. So to understand what the impact or basically overall implications of this mechanism would be, we have built a set of models to try to understand how different decisions about materials and pavements can change the total amount of carbon uptake that would occur over time. So there are a number of different factors that can influence that, but a couple of the critical ones are the amount of exposed surface area. Obviously, if there's more surface area, there's more opportunity for CO2 to diffuse in and be turned into carbonates. That, when we talk about pavements, translates fairly directly into what kinds of maintenance treatments happen to that pavement. So a common way that concrete pavements are maintained is to actually grind off some of the surface to re-smooth the pavement. That grinding off obviously exposes fresh surface area and reinvigorates the process. And finally, I'd just touch on one there at the end, which is the end of life treatment. This is again a surface area question. When we either tear up a pavement or we tear down a structure, that crushed concrete that results obviously creates many new exposed surfaces. And as a consequence, the rate of uptake at end of life can be much faster than it is during the use phase of a built structure or pavement. So we've taken those detailed models and we've simulated what the implications would be for concrete pavements in the US pavement network. This is a simulation out over 30 years. The blue represents the amount of carbon uptake that would occur during the use phase of the pavement, and the green represents the potential uptake that can occur at end of life. You can see our estimate is that carbon uptake in this case could offset about 5% of the clinker-related GHG emissions associated with that pavement. So that's a significant savings, then it's something that certainly should be managed for these types of structures. Let me just briefly touch on these other two mechanisms and how we've kind of modeled those and what their implications would be. So first, this pavement vehicle effect. Pavement vehicle interaction occurs for two reasons, either because of the stiffness of the pavement, so a less stiff pavement flexes and vehicles have to expend energy to overcome that flexure. It also occurs because of the roughness of the pavement. The rougher a pavement is, the more that I spend energy moving wheels up and down rather than forward. It turns out that different pavement materials have different amounts of stiffness and they degrade in terms of their roughness at different rates. Similarly, different pavement materials have different amounts of this so-called albedo effect. There are actually 2, 3, depending on how we count it, ways in which the albedo effect is climate relevant. One is this first very acute angle, and that is the amount of energy that comes in from the sun that is basically directly reflected right back out of the Earth's atmosphere. So that avoids general warming. It's what we would call radiative forcing effect. The other is that those reflective and thermal properties of the pavement alter the temperature around the pavement and alter the amount of radiation that hits adjacent buildings. And so that also changes the amount of energy that those buildings use, and therefore the CO2 that is associated with producing that energy. So we've actually built simulation models that allow us to capture this effect. This is actually a sort of map of Phoenix here. And each one of those green areas represents neighborhoods where the pavements in that neighborhood would have a lower total footprint if they were stiff and reflective pavements as opposed to darker and flexible pavements. And just to kind of give you a sense of what the scale of this analysis, these call outs to the left and the right are trying to indicate that to come up with this result, we've not only modeled every pavement in Phoenix, but actually every building next to every pavement within Phoenix. Now, I would just make one other point about this, and that's just simply because of the way that research progresses, is that despite, I talked to you for quite a while about all the strategies that are out there for reducing the footprint of cement and concrete, this benefit actually would accrue even with current mixes that have not been optimized to reduce GHG emissions. So again, a really exciting area where concrete can be a part of a sustainability solution. So we had these interesting results about the potential for carbonation, the potential for albedo, the potential for pavement vehicle interaction, and we had these different strategies that various groups have proposed for reducing the footprint of cement and concrete. And so we kind of asked the question, well, what would be the implication of those? And we did that by combining the simulation models that we have for the US pavement and building infrastructure with these types of scenarios of implementing these reduction strategies. So we actually looked at 3 scenarios. One we call 2017 level, which is essentially if we continue to produce cement and concrete as we have historically. One that we called projected implementation, where we implemented only the types of strategies that have already been identified by various industry groups or committed to by those groups. And then finally, one that we refer to as carbon neutral implementation, which applies those same strategies more aggressively, as well as the other types of strategies I mentioned earlier. So incorporating recycled concrete to be more efficient in its application during design, implementing best-in-class carbon capture and storage in the industry, and also some amount, only about 15 to 20% replacement of aggregate with those synthetic aggregates. And so we looked at these to understand, well, what is the real potential here for cement and concrete? So the plot on the left here with the bluish shading shows what we would anticipate as the reduced footprint associated with cubic meter of concrete produced through the projected scenario. And that shows some significant declines, going from about 350 kilograms per cubic meter down to about, say, 250. But we're much more excited about the plot on the right, which is that it shows that through selective application of these strategies, we could actually produce concrete mixtures with 0 net GHG associated with them per cubic meter produced. So what is the implication of that in the system as a whole? If we take those mixtures and we look at what their total life cycle implications are, we have some further very exciting results. So this is actually a simulation of the US pavement network. The black line here shows the historical GHG related emissions associated with that network. The dashed line shows with sort of what, like I was saying before, what if we just continued to do what we had been doing? And then I would just call out a couple of interesting simulation results. One is this sort of light red colored line here, which represents implementing those projected changes to cement concrete production. Some significant reductions there in future GHG emissions. But even more exciting is if we implemented that carbon neutral scenario, what's labeled here is the ambitious scenario, as well as implementing some additional funds into the pavement system in order to make sure that it could be stiffer, more reflective, and smooth. We could see as much as a 65% reduction in the GHG emissions associated with that system. What's particularly interesting is that this system here, in order to be stiffer, more reflective, and more smooth, actually contains about 3 times the amount of concrete as the system did at the beginning of the simulation. So it's a very clear example of concrete being a part of a sustainability solution. So just in conclusion here, I want to make one quick point and then highlight some of the key strategies. One is that it's critical when we talk about the performance of a material that we talk about it from a life cycle perspective, that the impacts are not just in the materials production, but can also occur from fairly surprising places during the use phase. So it's critical that we take a whole life perspective, not just looking at embodied emissions. In terms of the cement and concrete system, there are many opportunities out there to reduce the footprint and to ultimately become part of the sustainability solution. It's clear the industry's got to do the hard work of installing best-in-class technologies. They've got to make the investment and partner with others to mature and implement carbon capture and storage technologies. In terms of concrete, it's critical that we shift to performance-based standards to allow for innovation and therefore adoption for things like synthetic aggregates as well as low GHG mixtures. And when we talk about the life cycle as a whole, there are some really clear opportunities to have net negative applications of concrete, including stiff, smooth, and reflective pavements, energy efficient and resilient buildings, and structures that have been managed to maximize carbon uptake during use. And so with that, I'll just say thank you very much for the opportunity to present today.
I would like to thank our partner, Penware, Senator Mike Cuff, and MLA Richard Gottfried, our speakers, and of course, all of you for attending today. This webinar was recorded and is available on the PNBRC website at buildingresiliencecoalition.org and the PNBRC YouTube channel. We encourage you to share this with your networks and join us again as we continue to explore the benefits of cement, concrete, and the concrete masonry's contribution to sustainability. Thank you for joining us. Good day.